And now to finish off our sequence of writing recursive functions for our raw lists, I would like to write copy and filter, which we recall caused us a bit of grief when we wrote them iteratively. Actually, we can refresh our memory what those looked like. So here, we saw this clever trick we could use to write copy, but observed that it might take a long time to copy long lists. The so-called fast way required quite a bit of work and would be a bit of a debugging nightmare. And then for filter, things didn't get easier. And so filter has all of the same complicated logic that copy does and a bunch of extra because of all the different special cases that can arise. I think a real mess if it needed to be debugged, or if it needs to be augmented later, even if the code works correctly. If you wanted to improve it or change it for some other case, you'd have a real nightmare figuring out what everything does. You need a lot of comments to explain this code to some other programmer. And as I mentioned in the video about this, even my attempt to explain it verbally may not have landed very well for any of you watching it because, although I think the code works and I have my own way of conceptualizing it, it's always hard to get inside the head of some other programmer to explain it to them in a way that makes natural sense to them. That is a good reason to write simple, ideally sort of self-documenting code, because although you have to write complicated algorithms in life, if there's ever a time you can simplify something, it makes everything easier for you and every other programmer to work with the code. My goal today is to show that recursion has a wonderful strength over iteration for these copy and filter functions. So the goal of the copy and filter functions, as we recall, is to make, in the case of copy, to make a deep copy of my list. That means that when I'm done, this list L2 that I'm constructing with the copy function, when I'm done, I should have a brand new list with completely independent nodes, each of which is a copy of the corresponding node of the list that went in. So of course, I don't want a weird situation where L2 is secretly just an alias of L1. I don't want it to have all the same nodes as L1, even though that would superficially appear to be some kind of a copy. I want L2 to be its own completely distinct set of nodes containing all of the same things. And I'm going to try and break this down recursively. Okay, so actually what I'm going to do is I'm going to comment out part E so that I can test part D separately, because unlike the previous video, the compiler might get quite upset with me if I try and test filter without writing it. Okay, so copy. And I'm going to break this down recursively, just like I did before. So suppose, again, I'm going to draw my list out as a node followed by the rest. And I'm going to break this up into special cases. So the first special case is, how do I make a copy of an empty list? So eventually what I'm going to want to do is say, oh, how do I copy a list with 3 elements? Well, I make a copy of that first element and I attach it to a list which is the copy of these other 2 elements. How do I copy the 2 elements? Well, I make a copy of the first element and then I attach it to a copy of this smaller list. So I make the list smaller and smaller. And I guess I could argue that eventually I'm going to be asking for a copy of an empty list. So how do I copy an empty list? Well, that's pretty easy. I just return an empty list. So if you gave me an empty list, so the head pointer is null, I return you a null pointer because a copy of an empty list is an empty list. All right, so how do I copy a list with at least one element? And again, the logic I'm going to use is this. I give you a list with at least one element. So let's say it's the 17. I bring that down, I make a copy of that one element into a brand new node, and then what do I attach it to? Oh, I don't know, a copy of the rest. That's it. And I have a function I can call to do this. Maybe we sort of get the idea by now. If I have a function that does copying, I just call that function. So let's clean this up a little bit and see what we can do. So first, I'm going to make a copy of, I'm going to make node ptr new head, and we'll set that to be make shared. I'm going to make it a new node. And let's see, so this for now, I'm going to set the next pointer of this new node to be null, just while I get everything set up. So what I'm doing here is I guess we can draw it on the diagram for L2. I'm making a copy of the node containing the 17, so I want the same element as the current head of the list. All right, and then for now, I'm just going to make this a null pointer. Okay, I am going to write this out in a more verbose way than you might. There is actually sort of a one-liner solution here. You could just write this as one return statement and nothing else, but I'm going to write it across multiple lines. So then I make a copy of the rest of the list. So copy of the rest. And what I'm going to do now is use the copy function to make a copy of the rest. So this is the copy of the rest. And to do that, well, I'm going to copy the list starting at head arrow next, the remainder of my list. So I call my copy function, I give it head arrow next. And there it is. And then all I need to do is attach my new head to the copy of the rest. So new head arrow next is going to point into the copy of the remainder. So copy of rest. And then I return the new head. I didn't need a loop. I need an if statement. I did need a bunch of, I guess, initializations or assignments, although you can do this all in one line if you're clever. Basically, what you do is you take this and just stick it into the constructor here, and then just return, instead of storing it in a variable, just return the result of make shared. But as usual, saving a couple of lines is just a question of personal preference. Writing 3 lines isn't really any more work than writing one long line. Let's see what happens if I try compiling this. We're getting the warning about filter not being written. Yeah, we're getting there. Let's see what happens if I run it. Okay, so what's part D doing? In part D, at the beginning of part D, we've got this list here, 17, 10, 6, and then 10, 3 copies of the element 10. In part D, I make a copy of L1 into L2, and then I add the element 999 to L1 and the element 1000 to L2, with the argument that if truly I have made a copy, I should end up with 2 distinct lists, one with 999 at the end, one with 1000. And I do. I have now made a copy of my list with my recursive copy function. And look at that. Comparing that to this enormous mess, that is amazing. That is beautiful. It is about the same length as the sort of clever solution iteratively, but you still need this loop in the iterative version, and this clever solution relies on insert at end. And finally, this solution is actually going to be a bit slower, because every time I insert a new element, as I mentioned in the video about this, I have to walk all the way to the end of the list. This has all of the speed of the fast but tedious way, but none of the complexity. All of the complexity is covered up in the recursion. And I think that that is beautiful. So let's move on and talk about the filter function. The filter function, if we didn't already have a headache writing the copy function iteratively, I think the filter function certainly gave us one. So I'm also going to clean up my diagram a little bit here. So I want to write the filter function, and recall that the goal of the filter function is we take a list and we take some element. We are now going to make a copy of the list that was provided with all copies of that element omitted. So if I make a copy of, for example, the list, here's the list L1 at the end of part D. If I make a copy of the list L1 with the element 10 omitted, I should get a list that is 17, 6, 999. So all of the copies of the element 10 are gone. I'm going to use the same logic I did for the copy function. In fact, just like I did with the iterative case, I'm going to try and steal some of that logic and use that as a sort of template. All right, so I would like to filter a list. I want to remove all copies of filter value, or make a copy without copies of filter value included, of a list that you gave me. If the list is empty, the result is going to be empty. I don't need to filter out any nodes if there's nothing in the list to begin with. So you ask me to filter a list that's empty, I return a null pointer, so we're already good. All right. Well, what else do I do? Well, in this case, there are 2 special cases I have to worry about, I guess, which is, what if the element I'm filtering out is the one I'm looking at? Well, in that case, I don't want to make a copy of that node at all. Alternatively, what if the element I want to filter out isn't the one I'm looking at? So 17 isn't being filtered out. Well, then I do want to make a copy of the node 17. So in the filter function, I'll need two cases. So if head arrow element is equal to filter value, then I guess I don't want to include, I guess I want to say this node in the result. Otherwise, the element that I'm currently looking at should be included in the result, because any value not equal to filter value should be included. So I now have 2 cases. I'm going to just leave this here, and then I'm going to sort of copy it. I guess we'll bring it up here. And so I'm going to work with the case where the element I'm looking at is in the result first. And there's a reason for that, because this second case, where I'm not filtering out the element I'm looking at, it looks a lot like what I did with copy. So if I'm filtering out the value 10, and I'm looking at the node 17, well, then I do want 17 to be part of L2. Just like in the case where I'm copying it. That's how I'm going to work on that one first. Okay, so the new head is going to be equal to a node that I create with the same element as the node that I was given. And then I say, well, okay, the copy of the rest, I'm going to say the rest filtered. Then I call the filter function to filter the element I was given out of the remainder of the list. And so I call the filter function here. It's going to be filter. I give it the rest of the list, so head arrow next. And I say I want to use the same filter value. And then just like before, all I have left to do, I guess what I have as of this point is sort of this situation. All I have to do is now set up the node that I created, the new head, to point at the filtered copy of the rest of the list. So I'll say rest filtered. And then I return the new head. Okay, there's one case. Now the other case is actually a little bit simpler. The other case is, suppose the thing I'm filtering out is the thing I'm looking at. Well, in that case, I don't want this to be included. All I want is to return, I guess we could write it sort of like this. I just want to return the filtered copy of the remainder of the list. I just skip over the node that I'm working with. And so I think in this case, all I have to do is return the result of filtering the rest of the list. And that's it. And so we'll take a look. We'll see if that works. Okay, no warnings. We run it, and sure enough, there it is. So we'll go down to main and look at the testing code. There's L1, so the first thing I print out is L1. I want to filter out the value 10, so all of these, and this, and I do that. There's the filter function. My recursive filter function looks like this. And remember what a nightmare it was to write copy and filter iteratively. It was nasty. And yet, let's see if we can put them both on the same screen. We'll just get rid of the terminal. Okay, so let's see if we can find, there is the code for my copy function, the iterative and fast version of the copy function, and there's my recursive code. Not only is the recursive code shorter, and it could be even shorter still, this could be written as a 4-liner because all 3 of these lines can actually be combined into one line, so we shouldn't worry about the number of lines. But I would argue, if you look at the complexity, all the calls to make shared, all the needs to adjust pointers, the structure of this loop, the meaning of these 2 variables, compared to this, which I think is elegant and beautiful, and a lot easier to explain to somebody who understands recursion. I think that it's night and day. And if it's not night and day already, if it's just dawn and twilight, then let's take a look at filter. Here is the tedious filter function. Let's see if I can cram them both onto the same screen. So we'll just get all the curly brackets. I cannot even fit both implementations on the same screen because of how big the tedious version of filter is. Even if I remove new lines, there's still an absolute nightmare left to scroll through. So many special cases. This entire extra loop that took so much extra explaining that I probably couldn't describe even to a colleague of mine because of how complicated the logic is without having to write a comment after every single line. Versus what I wrote up here, which, although it's not trivial, didn't require as much explanation. It only required me to break it into obvious cases. How do I filter an empty list? Well, I do nothing. How do I filter out the current node if the current node is the filter value? How do I filter if the current node isn't the filter value? That's it. Not all of these extra loops and the need to do all this bookkeeping. And that's one reason why when you're working with an application that admits some kind of recursive decomposition, especially a singly linked list, recursion is beautiful.